Hello everyone, my name is Abhishek Bansal. In this video, I am going to talk on the flyback transformer. How should we make a flyback transformer to be to give us a maximum efficiency? So before I go to flyback, what affects the flyback transformer efficiency, I am going to talk generalized what is basically that what are basically the terminologies for a general transformer, whether it's a flyback or let's say we are going to use it in a phase shift or an LLC or a multi resonant. So what are basically the transformer general design factors? So when we are designing a transformer, we see what is the relationship to the transformer power handling capability or an ability. Okay, so like we will see that when the manufacturer basically uses a different kind of code numbers basically. Okay, let's go this way only. Okay, so when we have to basically design a flyback transformer, as I have shown you window utilization, different kind of bobbins, so we are facing a different set of constraints, and one that could be dictated by basically an output power. Okay, so it's going to like what is going to be an operating voltage, what's going to be the maximum current, okay, that the secondary winding should be capable of delivering to the load. Okay, and obviously above that we have standards like CE, UL, VDE. We have regulation limits also. So we need to relate these constants at how much efficiency we are going to get when designing it. Okay, so like what would be the maximum permissible temperature rise of the transformer. Okay, so first thing that we have to select is basically we have to select the core material. What material we are going to use it, because we have a magnetic core made of an magnesil. It has a different permeability, it has a different permeability, like permeability for a iron alloy. The iron alloy is a material here. Sorry, the material is basically magnesil, but we are using the for an iron alloy could be of magnesil or an orthanol or the permalloy. So these are all having a different kind of operating frequencies. These are also having a different kind of coercive forces, Curie temperatures, or the flux density or the permeability. Similarly, if we are going to use a amorphous, we have a different, the popular material names that are used are the 2714A and then 2605, and we have an Vitropalm 500. If we are going to use a ferrite, we are going to have a manganese zinc, and we are going to have a nickel zinc. Okay, so these are basically, we see that even with the materials here, we have different materials here with different kind of magnetic materials. They have a different characteristics. Their characteristics are different in the permeability, their characteristics are different in the flux density, operating frequency, Curie temperature, and the coercive force. So when we are designing, we sometimes some particular manufacturer have a secret rule of the thumb. Okay, basically when we are designing because it's too much complicated, So an easiest way, every manufacturer, it's not even a secret that everybody is going to do design with respect to the current density. Okay, so typical assumption that is basically made is that we need a 2 ampere 200 ampere amps, not ampere, 200, or rather take per ampere we should take a 1000 circular mills, because if we are going to even design, you would have to select an imperial units or that, whether it's an MIL or an MM. So let's talk on the MIL only. So in this there per ampere there should be 1000 circular mills. Okay, so this is going to work in most of the cases and is going to keep you on the job, it won't fire you. So the next thing that we need to decide is basically the wire size. Okay, and I have mentioned, thus this is, we are going to see what is basically the power handling or the power handling ability or the capability we needed. So what we are basically doing, we first decided area product. It's called as an area product, AP, and it is equal to the window area, WA, and the cross section area, AC. Okay, so if I have to go, if I can say, okay, the power handling, because each core has some particular level of power handling capability. So that is basically related to this area product, and this area product is then going to be equal to power into 10 raised to power 4 divided by the power into 10 raised to power 4 divided by Kf, Ku, Bm, J and F. This is basically a waveform coefficient if you are having a sine wave or a square wave. Again, if you will see, it's those who says, okay, what it matters by 0.1, 0.2, you see that this Kf, which is the waveform coefficient for a square wave, is 4, whereas for a sine wave it's 4.44. So again it's a 0.44 difference only, and so the other thing that we have to see basically what would be its relation with the given temperature rise. Okay, so the regulation and the power handling ability of the core we can very easily going to relate it by some constant. Let's say, okay, the alpha is the regulation constant in percentage, and that is basically going to be equal to power upon twice kg ke, and the constant kg is basically determined by the core geometry, and the core geometry I will take it separately. So from that you can say, okay, that this kg is basically equal to window area into cross sectional area square into Ku upon this kg is basically equal to window area cross sectional area square Ku upon mean path length. Okay. Similarly, the other constant that I have taken in this alpha, one was the kg, the other I have taken ke, the into one half of this. So this Ke basically is determined by the magnetic and the electric operating conditions, and here again the Ke is basically what, 0.145 K square F, Kf square, sorry, and the frequency square multiplied by this Bm square into 10 to the power minus 4. Okay, and again this Kf I have said it's a waveform coefficient. Okay, so now let's again take what is basically a area product. So the area product AP. Okay, now if suppose I have the core here, this is the core, and this inside is the window area, and this let us denote it by F, this much, this by E, okay, and this length from here to here, this length let it be by G. Okay, so here I am taking a C core, we get the WA is what, F into G, simple mathematics, rectangle F into G. We see the AC, the cross sectional area is equal to DE, obviously it will be centimeter square what you will be taking. If I am going to take an area product, I have mentioned it's a window area into the cross section area. So this would be centimeter. If I am taking a centimeter square here, it would be centimeter 4. Okay. So again now we can relate the transformer volume and the product area. So the volume of the transformer, okay, what would be the volume? Now suppose I am going to use a toroidal core here. So the toroidal is going to be in this manner. Okay, the toroidal would be in this manner. So we are having an outside diameter here, we are having a volume here, we are having an height here. Okay, if I am going to use a popular linear transformer or an EI core, very well we know is that this internal, this would be the volume. Okay, so volume can be related to an area product. Okay, and like we are going to have a core type pod core, podded core, or we are going to have a lamination C core. So these all have a particular kind of constant values, like that the pod core, the relation, the volume to area product relation value is the 14.5. For a C core it's a 17.9. Okay. Now I have previously related now I can relate this area product to the weight of the transformer also. The weight of the transformer, let's say the weight is basically, WT is equal to K3 by L3. I am taking this here. Okay. So we basically, rather than going to mathematics, because I just want to draw that we are having a particular type, we have a particular type of core, and we have some values which is basically related to the volume and to the area product. We have a table with the volume with the weight to the area product. Like what would be the what would be the value for the code types that I have taken for the volume to an area product? We can similarly use the same codes to calculate the value for the weight to the area product. So I have compared the volume, compared the weight. Now we can similarly take the next factor, the transformer surface area to the area product. Okay, we can similarly, one is the weight, now we can take the surface area also. The other thing is that so these are the basically these things you want generally find it. The main part that you are going to see basically is related to the current density. Okay, so for the current density, it's very simple. Okay, how much current is basically required, but we know that the J is basically what? Now it's not equal to an I, it's an I by A. Okay, let me write all the equations then, it would be better. Okay, so we know that that we are going to have an area product, it's an AP, we have a current density J of a transformer, and we are calculating in respect for a given temperature rise. So we have an AT here. AT is basically equal to Ks AP raised to power 0.5, or basically it's a Ks under, it's a Ks under root of an AP, and we are having a copper here called I square R. I square R, I is equal to AW JMs. Okay, so the copper loss that we are using I square R is basically going to become A square W J square R, and we know this R is basically the mean path length upon AW into N into rho. Okay, so here we are assuming that the copper loss is the same as the copper loss during the operation for an optimized transformer operation. So basically, if we are going to put I haven't neither I am writing properly. So okay, let's come to the main point, the flyback only, because I wanted to actually go from here. Okay, let me do the core loss properly first. I was getting a bit lazy here. So here let's draw the copper loss here. Okay, so we can basically see, okay, in the current transformer loss, if I am going to put all these I am going to put all the values, what basically I am going to write, the copper is loss is basically AW J square K5 under root of an AP, not under root of an AP but AP raised to power 0.25, so it's basically 1 by 4 AP into N into rho. Okay, so what basically a flyback transformer efficiency is going to affect it, and this is basically what I mentioned in the, done lot of calculations there in the table. So that are not the data, that are basically the table manually or the calculator used to calculations. So what are basically the flyback transformer in the context of, let's take only the flyback transformer only. So the flyback transformer, basically we are going to say it has four kind of losses here: core loss, copper loss, that's a winding loss. We have not only these, we have a transition loss also, we are having an external loss also. So this core loss is going to occur in the transformer's ferrite core, and it is going to depend upon the core flux density. And we know, as we are using an SMPS here, we are using the switching mode, we are using a flyback topology, so it's going to depend on the duty cycle also. So okay, it's going to depend on the duty cycle, and it's going to definitely depend on the flux density, rate of change of the flux density. Okay, so this core loss is depending on the core flux density, is going to depend upon the frequency of operation. What frequency you are going to use it is going to depend upon the core size of or the volume. I have just talked on the core size and the volume, and it is going to depend upon definitely what are the properties of the ferrite material, because I have already mentioned that we have a different materials, and they are basically optimized for to use if you are going to operate the transformer at this frequency. It's optimized to be used for that particular frequency only, and it's even optimized to have a peak flux density. Okay, and that's going to exhibit a different kind of core loss. So these losses are basically occur at what we are going to have a flyback in the flyback power stage. This was the external losses, transition loss and external loss. So next thing, if we want to take the copper loss, okay, let's go into one more thing on the core loss itself only, because I haven't completed the core loss. So in the core loss, I have to say that when initially or the traditionally or the classically, when we are going to take, the designers basically the DC flux is not going to affect the core loss in an inductor. Okay, they only used to consider it only be it going to be that the losses are independent of the flux density waveform. But as I have shown in the flyback video also, that in an inductor, whether it's I'm taking a continuous waveform, or if I am taking a discontinuous mode, or if I am taking a boundary mode. Okay, if I am taking a boundary mode, I should rather draw it in this manner. Actually, this will become okay. This, if I am going to draw, or if I am going to use this. Okay, so when we are going to see, we see that the flyback flux density waveform is not sinusoidal. Okay, and it contains a significant DC component. So when we are calculating the core loss, we neglect the DC component, but it has a significant DC component. Okay, when I have already stated that this core loss is dependent on the flux density, the frequency, the core size, volume, and obviously the material of the ferrite. But when we are manually calculating it, we are basically ignoring the DC flux or the DC component. But here we can see it's non-sinusoidal, and it contains a significant DC component. Okay, so another assumption which gives us, this is basically the foundation of it's basically non-linear only. Okay, it shows that it's not linear, it's not following everything similarly only, because if I am going to change the duty cycle, this is for the one duty cycle. I mentioned, okay, suppose I am going to use it to less than 0.5. If I am going, but with the change of duty cycle, and similarly if I am going to use a different DC bias, it's going to give us same waveform, but in practically do not give the same waveform. So that is also linearity one assumes, because we that's basically an assumption which is basically made, that all waveforms are going to be, that all the waveforms regardless of the duty cycle and the DC bias is going to have the same core loss, because one can argue because they're going to have the same peak peak to peak or peak flux density swing. Okay, so so one assumption was that you are neglecting a DC component, assuming it's negligible, whereas you found it's as a significant. Another is that it's non-sinusoidal. Another is that with the variation of the duty cycle, this core loss is not same. It's variable with respect to the core loss, and it should be apparent that the eddy currents that's induced in the core, they are higher when the rate of change of flux is faster. It's quite obvious also, if we are going to have a faster rate of flux change, we are going to have a high eddy currents. Okay, because this eddy current is going to is getting driven by the induced voltage, and that would be again in high. Thus, compared to the eddy current loss, which would be generated by the sine wave of equal frequency, a low duty cycle rectangular waveform must generate a higher eddy current loss in the core. Okay, the another thing is that the magnetic cores, I should basically I have not spoken this very clearly what it basically, okay, because okay I am not going to read my own lines. Okay, so basically what it is basically is saying that the eddy currents induced in the core are going to be high when the rate of flux change is going to be faster, because since the induced voltage that's going to drive the eddy currents, that's going to be in higher, and thus when we are comparing with the eddy current loss that's going to be generated by, which is basically generated by the sine wave of equal frequency, a low duty cycle rectangular voltage waveform generating an equal peak to peak flux density must generate higher eddy current loss in the core. And the lastly in this is that the magnetic core, the magnetic domains, the domains was they are causing a non-uniform flux density, so that's going to result in an eddy current loss. Okay, which results in eddy current losses in excess of those which are related to the material's conductivity. Okay, and let me talk more on this. We have now, let's take a rectangular waveform with a variable duty cycle. Okay, I am just sticking still to the core loss only. When I am taking a variable duty cycle, now we are having a let's say we want to, okay, let's go to the ratio of the core loss under rectangular wave excitation to that of the sinusoidal wave excitation of equal flux. We will find it's like this way. It's like quite of a, I am not going to define exactly what it's a, you can see it's a quadratic or a parabola like you open up here. Okay, and this is basically, you can see that You can again the curve fitting equations have been used here. And for different materials we have found out the value. And lastly there is an effect of a DC bias, that the effect on the core losses when we are adding a DC bias for the rectangular waveform excitation. Okay, so what is basically what we want to say is that the factors that are generally taken or assumed that okay, that's not going to cause any effect because we are going to have a same peak flux density, it does not hold practically. Okay, so this is what basically these graphs are stated, because it's a study not done by me, there are many resources. Okay, and now let's come to the copper loss. We know that an flow of the current through the resistance of the winding is going to cause a winding loss or a copper loss. Okay, and it again based on the copper loss again based on into the DC loss and an AC loss, because the DC loss is going to be caused by the DC or the low frequency RMS current that's flowing through the DC resistance, or the basically you would have the DCR through the DCR of the winding. And if we want to minimize the DCR because we want to minimize the DC resistance, this is the DC resistance of the winding, so if we want to minimize it, so we have to maximize the cross sectional area and we have to minimize the wire length, and when we do these two things it will minimize this DCR. The other thing with the copper loss based on into it gets broken down into an AC loss, so that is caused by an high frequency electromagnetic effects from the magnetic field that's produced by the time variant current flowing in the wire. The third I have talked in the transformer efficiency is the transition loss, that's basically associated with the transition or the commutation of the transformer current from the primary to the secondary winding, because in this region the rate of the change of the currents is very high, so the currents will have large frequency harmonic component, and also the primary and the secondary currents they are flowing simultaneously, so here the it's going to behave like a high frequency transformer like other conventional high frequency transformers, and so this high frequency is going to affect and is going to cause a significant loss. Okay, so now we can also consider we should consider the two external loss factors. Okay, because that's due to the parasitic elements of the transformer. One is the leakage inductance, and because the leakage inductance it results in the loss that's incurred in the external clamp circuit, or we are going to have a snubber circuit. Okay, and they are necessary to keep the voltage stress on the primary switch below its maximum rating, that's the VDS, voltage drain to source. And the secondly we have to take the external external loss factor is the transformer capacitance, because transformer capacitance also no one talks of it, because that's also contribute to the total parasitic capacitance of the total parasitic capacitance. And if we are going to increase in the switching node or not or if there is an increase in the switching node capacitance, it is going to increase the primary losses in the primary switch. So we have seen that the transformer efficiency gets affected by these things, and one I can talk on the skin effect also. Okay, one thing that we should very must be very clear that we have a significant DC the current that are flowing through the primary or the secondary, they have a significant DC component, and they have a significant high frequency harmonic component also. So we have the copper loss that I have divided into an AC and an DC, or we are taking the DC resistance of the winding here or an AC resistance of the winding. So the ACR to DCR ratio is going to depend on the frequency, wire diameter, and the overall layer structure. Okay, so the eddy currents that are induced in the wires, because the eddy currents, why the eddy currents induced, because as a result of the magnetic field inside the wire, and they are the main cause of the losses, AC losses, because they increase ACR. Okay, and these AC, or basically these eddy currents only, they lead to skin effect and the proximity effect. So when a DC current is flowing in a wire, the current density is basically uniform throughout the wire cross section, or we can say the current is basically equally distributed. This is the wire only, so this is the current is basically distributed equally across the wire. And when we have a time varying AC current flowing, the changing current is going to produce a changing magnetic field around the wire, and this changing magnetic field, according to the Farad law, voltage would get induced, okay, so as to oppose the changing magnetic field. So this induced voltage, it causes circulating eddy currents to flow, and since the conductivity of the copper is high, so these currents can be high. Okay, not high, but these are rather very significant. And as the frequency of the AC current is going to increase, the current is going to become more concentrated near the suppose this is a cross section, so the current is going to get concentrated across the outer edges of the wire, and the central portion, okay, so suppose this is the current, so the central portion will have zero current as the frequency is going to get increased. So it defined as the depth inside the wire, the skin depth is defined as the depth inside the wire when the current density has fallen to approximately 37% of the value at the surface. Okay, one can similarly talk on the penetration depth, because the penetration depth is denoted by delta, and it depends upon the resistivity of the wire material, the relative permeability of the wire material, and the frequency. Okay, so let's talk on the proximity effect. Okay, but I have talked upon the skin effect. I have taken a single wire here, but we are not going to, the flyback transformer is going to consist of windings, it's not going to consist of single wire, so they are going to consist of multiple turns that is going to be built up in the multiple layers. Okay, we are similarly going to have secondary winding also. Similarly, we are going to have some, we will see, I will show you in the construction, we will have a auxiliary winding, and similarly sometimes we have a multiple of secondary windings. So here the skin effect alone is not significant. Here what we also encounter the proximity effect. It also is similar to the skin effect only, but it arises from the fact of the magnetic field that the AC current flow in one wire, it causes on adjacent wires. So we can see the proximity effect can build up rapidly because we are going to use more and more layers, and it can rise to that level, that to the point the inner layers are carrying the significantly more eddy current than the load current. Okay, so this proximity effect carrying the more eddy current than the load current, and we can this was a single layer transformer. We can talk on similarly a multiple layer, 2 layers, or a passive layers. Okay, now let's talk on the leakage inductance. So the leakage inductance is basically caused by the magnetic flux from one winding in a transformer that is not coupling to the other windings. So it's caused due to magnetic flux in the space and the gap between the windings that's going to store energy between those gaps. Is going to store energy between those gaps. The leakage inductance. So and it's going to store in the same way. If I am using an air gap core here, so here also the energy is going to get stored in the air gap of this core. So the energy of this leakage inductance is basically dissipated in the external to the core, and minimizing this leakage inductance very important for having a high efficiency of the flyback transformer. And as I have talked in the flyback operation also, this we are going to use a snubber circuit, or we are using a clamp circuit here. Also we will have to see that we minimize the ratio of the leakage to the magnetizing inductance in order to minimize the amount of magnetic energy lost. Okay, so this leakage inductance I have said is the main factor here, and it depends on the geometry or the winding geometry rather, because we have seen that we will going to use an interleaving. We will have, so that's why we use interleaving, so that we have a minimum of an leakage inductance. Similarly, we will want to use a wider bobbin which has a wider width, so that we have a reduced leakage inductance. We can minimize turns, we can minimize the lengths per turn or the mean length per turn, and we can minimize the thickness. We can minimize the thickness of the spacing gap, we can minimize the thickness of the winding layer and the number of layers. So all this reduces the leakage inductance and it increases the efficiency of the flyback transformer. Okay, and I will take the transformer efficiency. One more video I am going to make on the transformer efficiency, because here I am not writing neither any of the equations, nor I am writing any of the, nor I am drawing anything. So I will make it a separate video. For this you would know that the flyback efficiency affect due to core loss, copper loss, and the factors which are basically considered for negligence are not considered. They play a very significant role in the transformer efficiency. Thank you.